Okay guys, so here's our power supply yet again, yeah, and part 3 videos come a lot sooner than I expected, and I just want to show you now. If I turn this power supply on, yeah, we'll power it up, and look what we've got. Yeah, it's working. So we've got 5 volts, 3.3 volts, we got 12.7, slightly high on the 12 volts actually now. 11.7 on the minus, 11.7 on the other 12 volts. The reason these are different, by the way, is there's a FET. I'll show you the maintenance circuit between the two, and I think that's what the difference is there. But that's within tolerance, yeah. So there we have it working. Now then, you want to know why it's working now and why it wasn't working before, yeah? Well, actually, the answer came to me last night. I do this sometimes, and I don't know, maybe you can relate to this. And I've spoken to some people who are programmers as well, and they also relate to this situation where I go to bed, and I'm not thinking about this, yeah, I just go to bed, and then I wake up like about 5 in the morning, it's still dark, yeah, and the answer is in my head to the problem, yeah, the answer is there, bang, like a light bulb. And often, very often, that answer is the correct one. And I have a friend who's a programmer who he explained he does this. I said, you know what? I do that as well. And another person, the third person I know who knows this, actually, I mean, back in the 90s, was a hacker. Yeah. And he also had this. So maybe this is a trait with people who diagnose faults. Yeah, that the brain works when you think it's switched off. So anyway, that's just a bit about me and the way my mind works. But let me now explain to you how I figured out what the problem was, yeah? Okay, so basically from yesterday, the evidence was all there. If you recall, on the second part of the video, I was measuring the voltage at the top end of the TL431, the programmable Xenia, and I had about 2 volts on it. Just get onto it again, you'll see it. I've actually got this green wire soldered to it now. I'll just go to the end of the green wire. So they are 2.1 volts, yeah, there. And then we looked at this resistor here that feeds the opto isolator. And on one end of it, we got 3.2 volts, yeah? And this is why we figured out the 2 volts was wrong. And on the other end of it, I got 8.6. And from that 3.2 and 8.6, we worked out the current flowing through the opto isolator was about 2.75 milliamps, yeah? And what I then did is, I took my bench power supply, yeah? And I injected into this 12 volts on the 12 volt rail. This being the voltage from here that feeds to the opto isolator, yeah? So I injected the voltage into there. We measured on the top end of the TL431 here what happened, yeah, and I'd predicted it would go to about 4.7 or between 4.5 and 5 anyway, yeah. So we can see it's 2, and when I put my power supply on, it goes up to 4.9, yeah, which is what we predicted. What I didn't do, but I know what's going to happen, is if I measure again across this resistor that feeds the opto isolator, yeah. So the resistor, one end of it is here. It's now 5.56, yeah? And the other end is now 11.5, okay? And from this, I knew that's what I'm going to find. This is how we can understand what is actually happening here. Okay, so let me just explain that to you. Okay, so I didn't measure that yesterday, but I knew what it was going to be when I kind of woke up in the night. I thought, I know what I'm going to find here, yeah. So on this resistor, this is the one that feeds the LED in the opto isolator now. We've now got 11.6 volts on this end of the resistor, yeah. And we've got, I think it was about 5.7 on the other end, 5.65, something like that, yeah. So we have about 5.7 on the other end here, yeah, 5.7 volts. 11.6 volts. So both voltages have gone up because I forced the 12 volts to 12 volts or close to it, yeah, to put more power into the circuit. But if you look at the difference between these two, It's now about 5.9 volts, yeah? Before it was about 5.5. And once again, we can work out from Ohm's law the current flowing through this LED in the opto isolator. Again, V, I, R in a triangle. So if you want to know I, it's V over R. If you wanted to know R, it's V over I. If you wanted to know V, it's I times R. That's why we use the triangle, yeah? So we want to know I again, so it's V over R, yeah? So I equals V over R, yeah? Which in this case is 5.9 over 2000 ohms, yeah? And this will give us the current flowing through the LED. And you can see straight away it's going to be a bit more than it was before, yeah? So let me just get the calculator and work that out. Okay, quick use of the calculator tells me that it's now 2.95 milliamps, was 2.75 milliamps. So all we've done by putting the correct voltage on here, which puts the correct voltage on here and makes this TL431 operate correctly, is we've just put a little bit more current through the LED, so it's now just a little bit brighter than it was before. So the signal going to the pulse width modulator controller hasn't changed, yeah? I'm thinking, oh, we've now changed it and this isn't responding. That isn't the case at all. That's not what's happening here. Now, just before I tell you what is happening, and you're probably a step ahead of me here, let me just explain what this circuit is about and why it is this way, yeah? I'll just tell you how this actually should work. So let's have a quick look at these TL431 circuits, yeah, and how they should work. So basically the TL431, you can think of it as a Zener diode, yeah, that starts to conduct at a certain voltage, but it's programmable. So on the reference pin, the third pin, you can use two resistors to put onto that pin a voltage on there, and that sets the Zener voltage, yeah? So the normal way a power supply would regulate the output voltage would be like this. So this is your output voltage, yeah? And coming from the output voltage, you would have a resistor, yeah, which goes to the opto isolator, yeah? So this is the LED and your opto isolator, yeah? And then that goes to your TL431. Your TL431 is here, yeah? Okay, and this is your program pin, and this goes to ground, yeah? This is your opto isolator, the LED here, yeah? And then from here you have another resistor up to the V out. We saw this on ours. This is so that this has always got a supply even when the LED isn't on, yeah? Otherwise it couldn't work. And then this pin here, normally you would take a resistor from the output voltage, the one you want to monitor, another resistor to ground, yeah, and this we connect to here. So this programs the voltage at which this turns on. Once you've set the voltage at which this turns on, yeah, say it was like set to 3 volts, yeah, when the voltage here goes above 3 volts and above the turn on voltage of the LED. So the LED turn on voltage, its forward bias, might be like 1.2 volts, yeah, 1.1, 1.2. So if the voltage up here, and this resistor will drop a bit of voltage as well, yeah, goes above 3, 4.2, let's say 5, depending on the value of this resistor, this will turn on, yeah, this will turn on, this LED will come on, yeah, and the thing will light up inside the opto isolator. It'll turn on the photo transistor, and this sends a signal to the pulse width modulator, a signal to say the voltage is up, we've got enough volts now. And then the pulse width modulator will kind of like back off, you know, because it doesn't want to increase the voltage anymore. It's got 5 volts and it wants 5 volts. And that's how it monitors that. So when you draw more current from this, the voltage here drops. This is constant, it's a reference. The LED goes dimmer or goes off, and the pulse width modulator then sends more power. It increases its duty cycle through the transformer, yeah, the switch mode power supply transformer. So that's how this would work, and that works fine. The problem with this circuit is when this voltage becomes low. Say you wanted to have a 3.3 volt supply, yeah, and not a 5 volt. The minimum voltage that can be here is 2.5, yeah. That's the minimum voltage that this Zener can be set to. The LED itself is going to drop 1.1, 1.2. So add that on top of that, and you're now up to 3.7. Yeah, and that's before you've got a little bit of voltage drop across this current limiting resistor as well. So this cannot regulate voltages anything really below about 5 volts. Yeah, it can't do it because of that. So there's like 3 ways around that really. One way is quite simple. You can get a TL431 or a similar that has a lower reference voltage. I had one that I was playing around with, which was a KA1431, and that was a 1.25 volt reference, not 2.5. So in this case, 1.25, 1.2, 2.45, that could regulate a 3.3 volt supply. Yeah, that's one way. Another way, using a TL431, is to do this with it. So here we use a transistor. Yeah, we use a PNP transistor. So we have a resistor down, PNP transistor, and here, yeah, and then this transistor switches on the opto-isolator LED. Okay. So again, this is inside the opto-isolator. Yeah, and then that goes to ground. Yeah. Okay, and then we have a resistor like this one feeding the TL431. Okay, and then that goes down to ground. So TL431, yeah. And this is your reference voltage, and again, you have 2 resistors setting that, yeah. Now, when this turns on, say this was set to turn on 2.5, that's its minimum, yeah. You've now, instead of got the LED being powered by this with a 1.2 volt drop, it's just switching the transistor on. And this transistor, base to emitter, it's probably got like 0.5 or 0.6, yeah. Let's say 0.6 volts, yeah. Voltage drop across there. 2.5 plus 0.6 is 3.1. You could have another 0.1 across this current limiter, and you could just about regulate a 3.3 volt power supply by that, yeah. When this turns the transistor on, the transistor powers the LED, yeah. So that's the second way to get around it, regulating a low voltage supply. The third way to do it is the way that the guys who designed our power supply did it. So what they've got is a 3.3 volt supply on the reference, yeah, but they're using a higher voltage supply, in this case the 12 volt, to power the LED. So that gets around the fact that you need more voltage to switch this LED on. If this reference 2.5, this supply is 12 or 11.5 or whatever it was, yeah. That's why they've done it this way. So they're monitoring a 3.3 volt supply, but they're not using the 3.3 volt supply to turn the LED on. They're using the 12 volt to power the LED. That's the third way around it, yeah. But in all of these cases, our LED is on. We've proven that. We've even looked at what current's flowing through it, yeah. And why is the LED on? Well, the evidence is here, and this is what I woke up realising this morning. And I knew if I measured these voltages here with my power supply attached, what I was going to find, yeah, that the LED was on and just a little bit brighter. So I woke up this morning and I thought, I hope somebody else doesn't think of that before I get to the office and make a video. And of course I'm going to my YouTube first thing this morning. Hi Josh C, how you doing, mate? Josh C, I hope you're a subscriber, by the way, and thanks very much for your input. And we were very much on the same lines with this. Josh C came on and said, Rich, have you thought of putting a load on the 3.3 volt supply? And that's what I thought. Previously on video 1, I put a load on this power supply on the 5 volts and on the 12 volts. I used a couple of hard drives, and I didn't know at the time it was monitoring the 3.3, yeah? So what's it doing? And Josh knew this. Do you know the ins and outs of it, mate? You may well do, yeah? The power supply comes on and the 3.3 comes on, and we know that because the analyzer all along this has been telling us that 3.3 is there. That's been staring us in the face. 3.3 is correct, yeah. So it turns on the 3.3 comes up, yeah. It turns this on and starts pulling current through this LED. This shines on the photo transistor, and it tells the pulse width modulator to back off. Back off, we've got enough power. So it backs off, it reduces the pulse width, the duty cycle of the pulses, it reduces them, yeah, to send less power into the transformer. So the voltages drop. And the voltages do drop, but the 3.3 doesn't. And the reason the 3.3 doesn't is quite clear if I take a voltmeter and measure the resistance on the power rails, yeah. So let me just get the plug of the power supply here, yeah. So if we go from ground, okay, and we go into the 5 volts, yeah, we read a resistance, yeah, kilo ohm or something, but there's a resistance there, yeah. And if we go on the 12 volts, which by the way on this I have to go to the 4-way, because if you remember the circuit diagram, this 12 volts comes straight from the transformer, and the other 12 volts rail for the 20 pin goes through a FET, and this FET's obviously off now, there's no power, yeah. If I go from this 12 volts here, my analyzer was just going full on the floor there, caught it with my arm. So if I go from the 12 volts here, yeah, 240 ohms, so there's some resistance on that. So basically some current will flow on both the 5 and the 12. If I go on to the 3.3 on here, look, it's just going up and up and up, the capacitor's charging, and eventually it'll just go over, yeah, it'll just charge up. There's no load at all on the 3.3, yeah, unless you connect a load. And that's why this power supply won't work, yeah. So the pulse width modulator controller throttles back, yeah, it reduces the width, but this voltage won't go down, and the reason it won't go down is because on here there's capacitors, yeah, to ground, and there's nothing drawing any power from it, so it can't go down. So eventually the power supply goes to its minimum pulse width, minimum duty cycle. All your voltages have dropped, but this one can't drop, and that's why it isn't working, yeah, that's why it won't work. So all along with this we've been chasing a phantom fault. I can only believe this is a compact power supply, yeah, and the designers of this power supply know it's going to a compact computer, yeah. It's not a general purpose ATX power supply. They know where this is going to go. They know what power is going to be drawn on the 3.3 volt supply, so they don't have to put any sort of load on that, because they know what's going to be drawn anyway, yeah. So there's no resistors built on this board to put a bit of a load on it. So what I did earlier, I'm just going to do again now, is I'm going to put some load on the 3.3 volt supply, yeah, and then we'll power it on. Okay, so I've wired this all up now. So this is the analyzer, obviously, 12 volts in the ATX 20. I've got a couple of hard drives, an IDE and a SATA. I think this is what I did on part 1. I might have used 2 IDEs, but I have tried it synth with 1 IDE and 1 SATA, and it still won't power on. I can't be sure if the SATA is even using the 3.3. It might be using the 5 and the 12, because that's all 3 voltages on here. It's possibly the 3.3 is only for SSDs or 2.5 inch drives. I don't know. So what I've done is I've put a resistor on the 3.3. So these 2 meter probes here, I've got into the black and into the orange, yeah. That's connecting to the orange on the ATX, yeah, on the ATX 20 to the black. And then I've clipped the meter leads with a couple of crocodile clip leads going to this resistor, and this resistor is 2 ohms 100 watt. Now on a 3.3 volt rail, 2 ohms law again, I'll draw about 1.5 amps, yeah. If it was 1 ohm it would be 3 amps, 3.3, yeah, and if it was 3.3 ohms it would be 1 amp, so it's in between, so it's about 1.5, 1.7, something like that, yeah. So that's a load on the 3.3. And now if we switch this power supply on, what we'll see is that it powers up. And the voltages are present. It's working now. And that's all it needed. So the thing was working all along. Yeah, the feedback circuit was doing exactly what it should do. So guys, what happened there? I mean, we spent a lot of hours analysing a fault that didn't exist. Yeah, really. And yeah, I think that was a very interesting and useful video. I know a lot more about feedback circuits now, about the TL431 and the way it works, and the reasons sometimes you have to get around certain difficulties if you're trying to regulate a low voltage relay like a 3.3. Yeah, I've also learned to load ATX power supplies properly if they're not working. In the past, I always just took a hard drive on the 5 and 12. It might be unusual that this regulates the 3.3. I think often it's the 12, but still, we've seen one, and I'm sure we'll see another one. Thanks to Josh. Josh C, nice one, mate. In a way, I didn't want to see that message this morning, but I'm glad you put that on there. It's good to see somebody's watching and looking at what's happening. Yeah, keeping an open mind, or they've seen this before. So I think it proves there's a lot to learn here. I'm learning, we're all learning. And I think it also proves that we can build a community here, you know. It's guys like you and your input. Sometimes, you know, I upload videos and I can't fix it. And then come along, you know, if you've got some ideas, you know, I'll always go back and try it, and maybe it didn't work, or maybe it did. Okay, guys, I'll be seeing you very soon on another video. And if this is the first one of mine you watched, subscribe, please. That's the first time I've ever asked on camera. Okay, guys, see you all soon now. Ciao.